So today, from RoboCorns 1423, we're talking about topology optimization. If you don't know what it is yet, I'm going to explain about it more. It has to do with part design and basically computational design process. So essentially what it's doing, if we think about CAD, so this model on the left might look like a lot of parts that people design, solid part, and it's like a bracket, let's say. But that bracket design is not very special. There's nothing too special about it. It's just a simple bracket. But what topology optimization does is, based on a certain set of objectives, it can change your design based on certain principles to create something that you may not have thought of originally while designing in CAD. The main process flow for this, we'll start with the discretization. And by the way, I'm going to explain each step, so don't worry. It starts with discretization of your model. And then a very core part of it is going to be the finite element analysis, which stems from the discretization. And then what will happen is your computer will evaluate the objectives that you set. And then it's going to check to see if you have reached the core model. If you haven't, it's going to repeat this process. But if you have, it's going to output your main design. So first, I'll start with discretization. What am I talking about when I say this? Essentially, what is done while doing topology optimization or finite element analysis is your model is going to be split up into a bunch of tiny elements. So if you look at this here, if you have like a trapezoid, it'll be split up into 3 triangles. And at the corners of the triangles, there are things called nodes. You can specify how many nodes there are in your system, and that'll define how many different little triangles you have. So this is an example of a wheel, and you could see all the very tiny triangles. There's many different ways that you can do this. You can have quadratic shapes, so you can have like a square one. You can base these off of different kind of lines. So if you're making a truss for like a bridge, you don't have to do triangles. You can just do lines and do like a pure bending analysis on the different lines. So there's many different ways to approach discretization, but for most FTC teams, you'll probably just use triangles with a fairly high node count for accuracy. So why do we break down the models into a bunch of different triangles? Well, this is so we can run finite element analysis. Essentially what this does is it's calculating a physics situation for a finite element of these different little triangles. And so if we look at, let's say, these wheels, you could put, let's say, pressure on the outside of the wheel, and you can fix the inside bore. So what that's doing is the fix is holding that wheel in place, and then you have pressure on the outside. That's your system. That's what you're trying to test your object for. So obviously it's not done in real life, but to be very accurate, it uses the very small triangles to essentially solve a really complex problem on a very small scale. So this is a very cool tool compared to general like hand analysis, because you can solve this physics situation for any kind of shape. So this enables the topology optimization to test the stress within your models for a very unique organic shape. So at the start of your topology optimization, there's something that you want to optimize. These are called your objective functions. So there's many different kinds. You can minimize the stress within your model. You can minimize the compliance within your model. So how much does it move? You can maximize your stiffness. So, it can't move. You want it to be very stiff. Or you can minimize your maximum temperature. That's if you're working with thermal applications. I've never worked with that in FTC, but if you're interested, it's there. And essentially what these do is they're the guideline for your optimization. So when your computer is trying to optimize your model, what do we actually want to accomplish? We want minimum stress. And so what your software setup is going to do is, through each step, it's going to see how close it is to getting to your objective. And you can see there's many steps, right? Step one, very basic model. But as you keep going through the steps, you're getting closer and closer to that optimal model. And that'll be very important later on. So these objectives are basically useless if you don't have constraints. So I'll raise a question, just a rhetorical question, but if you're thinking of a simple model, what is the most optimal design if you were to put a simple load like this force vector here? The most optimal design is this fully filled in box, right? You have the most material, and that means it's gonna, take stress the best, and it's not gonna move very much. That's your optimal design. So we're not looking for that when we're running this optimization, because we know that's the optimal design. That's our trivial design. And when we're working and we don't want to use a lot of material and we want to, save weight, this isn't going to help us. And so what we do is we're going to use what are called constraints. These are going to allow us to get that non-trivial design that you see down here, where a lot of material is removed. So some popular constraints are minimum volume fraction. That's just essentially setting how much material you want to have left after you run the process. So if this is 100%, let's say this is like 30%. Manufacturing constraints, that can be important. So if your 3D printer or your CNC mill or your 5-axis mill, I don't know, if that has a certain way that can only cut or produce your part, you might want to include that in your optimization. There's also maximum temperature as well. If you're working with thermal, you can have it optimized based on temperature. So after you set those, there's a lot of stuff that goes in between just to make sure the setup's correct. But after you define the constraints and objective, you'll essentially be able to you'll run the process, and your computer is going to figure out, did the model converge? So convergence is essentially the idea that your model has reached like the peak design, like this is optimal, and we're at the local minimum on our objective function, and we've successfully fulfilled the constraint. So convergence is good, but convergence may take a lot of steps. As I showed prior, the less steps you have, the further you'll be from the real converged model. Yeah, and so if it hasn't converged, your computer will just run next step, next step, next step. It may take like 100 steps. So as you might see, this is very computationally costly. So it's not, you may want to be wary on how much you run this, because it will take a little bit to get done. More steps you get, it'll get closer to the optimal. So some software that I personally use for this, there is other ones out there, but these ones have some educational programs that you can get access to the software for free. And Topology is one. That's the one I like to use because it has applications for more 3D printing stuff, and I'll get into that later. Abacus is really good. That's from Deso Systems, especially in their Simula line. That has good finite element and topology optimization. Altair Inspire, very easy to get your hands on. They have a very simple student access, and it has all the topology optimization and 3D modeling you need. SimScale is a very good finite element analysis tool. It's all web browser based. So for those of you who like to use Onshape, it integrates directly with it, and you can just import your models right out of there. You can do very basic analysis with it. So I explained how it works, but how does my team actually use it? So we're running Swerve this year, and the big thing we wanted to work on was the wheel. So this was our starting wheel design, just had some simple spokes. But as you can see, this wasn't going to turn out very well. I bet if I printed this out, I could break it with my hand. Not very good. This is the wheel that we've tested with our robot now, and it stays strong. It perfectly works. And we used finite element with just our own thinking to essentially strengthen the design. So that's one way where you don't have to print this and figure out, oh, it didn't work. You could just jump to something that does work. But we were looking at that and we knew we could do better. So if we think about in biology, how do our bones look like? And our bones are essentially formed with a shell that has a very strong bone, very thick in calcium. And that's like a shell. And then on the inside, there's this really complex lattice that forms. And that gives the bones their stiffness at the ends. And so I'm thinking, hey, this looks a lot like a 3D print. Why don't I try and optimize my 3D prints like my body optimizes my bones? As you can see, right, the shell is thinner in areas of less stress, and it's thicker in areas of more need. And the lattice also changes. So it's thicker on the outside where the stress is higher and thinner on the inside where it's lower. So in doing that, I think, okay, let me start doing topology optimization. This first one's done in Altair Inspire. So this wheel started as a fully filled in design. And my constraints, my objective is to minimize stress. And my constraints were you can only take out so much material, and you must take out material in this axis. So that is one of like the manufacturing constraints. If I want to 3D print this, I can't have weird overhangs. That's not going to be great for the design. And so I end up with this. And then, and that was, yeah, I ended up with that. And now what you're seeing here is the attempt to do lattice optimization. So we basically took the stress data and sliced it into four separate sections or quartiles. And we used the frequency and the amount of stress in each region to essentially splice together different thickness lattices. So when you're 3D printing, you can have like a 30% infill, 50%. That's essentially what we did here. And we also could track the weight. So we did lose significant weight as we added more regions and really did a bigger gradient. So as you can see, this is in Bamboo Studio when it's sliced all together. You can see the varying lattice thickness as we get towards the center. But in talking with some engineers and showing them the design, this isn't really the most optimal design because I made the constraint to extrude the axis. A more optimal design is found with our second optimization process. This is done in Topology. And again, we start with the fully filled in model, right? Our most optimal solution without optimization. And then we ended up with this design. So I add the volume constraint, but I also don't have the extrude constraint. And that gives us this sort of I shape, which makes some sense because if you think about things that bend and move, if you have like a pure beam, the most stiff beam is going to be one where the material is further out and kind of in this disc shape. Same with the wheel. If your pressure is coming here, you want a lot of material stacked there. And if you don't want it to bend, you need this kind of shape here. So this is a way more optimal design than what was before. And if we look at how we did the lattice, Topology is built to do complex lattice systems because it's all done implicitly. So there's no real meshing. So right with this lattice, how I showed you earlier and talked about discretization, that's really costly, right? You have to make all those little triangles. And so in making a lattice in Topology, it doesn't use the triangles. It just uses equations. And what we did with that, and because Topology is powerful for this, we're able to change the thickness in a gradient style. So we use, again, the stress point map or like our stress data, and we can drive the thickness based on the data. So in areas of lower stress, the struts will be thinner, and in areas of higher stress, the struts will be thicker. And that is filling in our original optimized shape. And then again with the shell, as we look, and I talked about the bone earlier, we need something to surround this mesh to hold it together. And so we can use a shell that is also driven by thickness or driven by stress and to change the thickness. So in areas of lower stress, it's thinner, and in areas higher stress, it's thicker. And this is all done with computer. I don't have to do any manual calculation. I have to know what the computer's doing, but I can just tell it to drive it, and it helps us end up with this optimal solution. So if there's anything I leave you guys off with, I'll say topology optimization is a great way to learn about computational design and to kind of break into that sphere, because there's a lot that is possible, and I barely broke the surface. There's so many things you can do, and you can also write your own code to do it. And there's also way more ways you can analyze a situation than just a simple stress and volume. I advise for FTC to stick to simple applications, but ones that would be effective, kind of like how we did the wheel, because you might have a really complex shape, but if it's hard, if you can't like imagine the physical scenario, you have trouble like diagramming it even on paper, it may not be the best thing to learn optimization with, because you'll get an answer and you won't really know if that was a real convergence on the optimal design. I also say that there are many ways you can do optimization. As I showed, there's a bunch of software. Each of them might give you a little bit different of a result, and you might think of different ways to actually run the process, different functions that might get you a similar result. And so I say take multiple attempts when you're doing this. You saw I did 2, and I learned a lot from the first one. That was my first attempt at doing this, and I made progress, but I learned like, hey, this is really what I want to do instead of doing it this way. And I think by just trying it, you'll learn a lot about what you know and what you can actually do with the software. And to actually track like your progress, I say track your, if you're, let's say, getting rid of volume, track each step, see how well it holds up stress wise, see how much volume you took away, and see, as I get rid of volume, how is my model holding up? Because that's how you're going to track your progress if you want to really find the optimal solution. And again, that's just iteration. This takes process just like normal design. But also keep in mind the actual technical stuff that goes behind the scene. I explained kind of what the computer does, but there's also a lot more to it. So it's great to look that up, reach out to people who have great expertise on, oh, this is, when you run this is actually what it's doing. So you have to take account for that. To know the specifics allows you to understand that when you run the process, because you're not going to have to think about discretization and all the complex like computer stuff while you do this. You can just apply it yourself, but it's important to know what it's actually doing. So when you do it yourself, you're not clueless about the answer you got. That's everything I had to share. If you have any questions, there's the email, and you can follow us on the Instagram if you want to ask questions later. But I'm open for questions now. I think I saw a hand raise. I don't know how to access that. Sarah, what is your question, if you had a question, unless you did not? Oh, I guess not. I see applause. Thank you.
I do have a question. What testing methods do you use to verify the performance of optimized parts?
So there's a lot of stuff computationally that I can do. And, that's mainly finite element. Once I get an optimized part, right, I just ran the process and I obtained it. If, let's say I chose a volume fraction of like 90%, I took away not much. I'll run the simulation and see what is the stress throughout it. And then I'll run it and see, did I get to something optimal? So I'll run 90%, 80%, 70%, 60%, and on. And I'll see what the stress looks like throughout the model. But, this is just the computer. So you have to take some of this stuff with a grain of salt, because if your simulation wasn't accurate, it might not transfer into real life. And so what's great about doing stuff with 3D prints especially as someone who's new to this, you don't have to waste money investing into like the complex metal part that you design for it to just break. But if you do a 3D print, you can track your progress using graphs and data and really see, oh, is the stress too high with this further removed model? And then when you actually make the model, you can test it and see, hey, is this what I expected? Or is this not what I expected? Should I go back and try like an older version, something that had less material removed? So I say just track each step as you go and make sure that you know the capability of each step.
Thank you.
I have one as well. Can you tell us, like, how does the design process differ from static versus dynamic robot components? Maybe.
Yeah, so the stuff I do mostly is all static analysis is what it's called. So the object isn't moving. And this is this stuff will work for stuff that moves. And if you're trying to make something move, it's very hard. And I don't advise people to do optimization with stuff that moves. It's really, I think it's mostly done with static situations. So if you have like a beam, right? Like let's say a bracket for your slides, let's say, and you want to hang with the bracket. The bracket's in a static sort of situation. And so it's not very hard to figure out how your forces and your fixed areas are going to work. So I say for FTC people, focus on doing static situations. But if, like with the wheel, they do roll, but you can kind of use a static scenario to optimize it. So I say stick with static sort of things to get better results.
Thank you.
Have you ever faced any challenges in manufacturing complex designs? And if you had, how did you address them?
Yeah, that's a really good question. So that's actually, I just solved that issue recently. I talked about Topology and how it uses implicit modeling to create the objects. The big issue with implicit modeling is that, let's say you design a lattice implicitly. Again, that has no discretization. So there's no triangles on that mesh and on that lattice that you made. So when you go to, let's say, 3D print it, you have to find very specific ways to convert the implicit into the normal explicit sort of model. Because if you have that lattice, the explicit way is to create a mesh which uses like a million triangles. I think when I did it, my computer shut down because it tried to generate 2 million triangles and couldn't do it. And so in using NTOP, they have integrations with Fusion 360. So if you know how to use Fusion 360 really well, Fusion can actually open implicit files. And so if you design something in NTOP, you could open it in Fusion and use their additive manufacturing capabilities. But if you're not good with Fusion like I am, because I'm not, what I did was I used Bamboo Studio to 3D print. So I would just import the shell and the optimized region because I can mesh that with triangles and not crash my computer. But for the lattice, I just imported the region that it had, and it can mesh the region. So it's not the actual lattice itself. It's just the space that it fills. I can import that into Bamboo Studio, and then you can make that into the lattice. And so that's how I solved the problem. It is definitely an issue. Sometimes it's hard to make these parts.
Are there any more questions? If not, I want to thank you so much, Kupor, for your insightful presentation, and I'm sure everyone learned something from it.
Yeah, thank you. Thanks for having me on.